Hi everyone, my name is Krish, and today we're going to tackle a paper which is much more fundamental in architecture, and it actually tackles the sparsity of a transformer itself. And of course, it's a paper by Google DeepMind, and it is a paper that I saw at NeurIPS in December. So let's just cover what exactly is sparsity in a sense, just briefly, and then we can understand my core understanding of this paper itself. When we sometimes understand sparsity, it usually has this tendency of switching off the neurons in a transformer on the basis of top k. Now, top k as a technology in very simple terms is just figuring out which are the most active neurons, and we're just going to keep them, and then we're just going to effectively turn off or reduce the influence of all the other neurons. But the main issue with top K itself is the sorting that is required of the neurons and the attention and the weights itself first. So that sorting actually leads to a lot of latency and a much higher complexity. So even if you expect that you'll save compute by using sparsity and have lesser number of neurons, but due to the inherent complexity of top K as a operation itself, it is about I believe so it's like O n log n. It is comparatively much more expensive in like huge transformer based architectures. So that's why sparsity is something that was needed to be re-explored, and that's what this paper did. A spark transformer, a very inherent change in architecture that helps us to look into transformers in a whole new spark. So let's just pick it up. Firstly, let's just look at the first graph over here. Here we're just comparing ReLU, Spark FFN, Top K, and ReLU square, and comparing them with the basis of the flops per token and the quality with which we're comparing it with. So in the first leg of the paper itself, they're just telling us what exactly worked with Spark. And one of the major things to highlight over here is that Spark itself was trained on a standard Gemma 2 schema. So basically it was trained on the same way Gemma 2 itself was trained, but instead of using like the simple ReLU or GeLU in that sense, also as a fundamental layer or a fundamental feed forward network, we're going to use our Spark, FFN, and Spark attention instead. So let's just figure out one of the more basic challenges in this paper itself. And I understand that this paper is much more dense in terms of mathematic angle and a lot of like theory heavy, and also has a lot of angles which need a lot of context in your mind as well. So I'm gonna go comparatively slow in this because I need to like understand it myself as well, side by side. So one of the first things that we come across is ReLU itself. When we use ReLU, it inherently is used a lot in sparsity, but it leads us losing a lot of essence itself because of ReLU's nature of actually turning off a lot of neurons. It has this natural tendency to help in sparsity, but it leads to the degradation of the model quality. And that's the first challenge that we figure out in the natural sparsity that we usually use, right? And secondly, like I said, the top K thresholding methods at the moment also introduce a non-differentiability that compromises the model quality again. And since it involves sorting, it leads to a lot of like compute because of that sorting itself. And thirdly, the inclusion of sparsity predictor often increases training pipeline complexity and incurs additional training costs. I think that's pretty self-explanatory. But let's move forward in terms of what exactly Spark Transformer itself brings to the table. So, on a very abstract level, one of the first things that they introduce as a new approach is a statistical top K operator. It basically works on the basis of arranging all of the neurons or all of the key things which are getting activated in a Gaussian distribution, and using the central limit theorem to understand a very flexible threshold over which we can actually use top K again. But we're going to cover that much more in detail soon. But also, we just, like I said, the Spark transformer itself is fully pre-trained using the Gemma 2 recipe, just to have this basic level of comparison fixated in the start. So let's get on with the actual architecture and the difference that Spark transformer has in terms of architecture itself. This is one of the more major images in this entire paper, but we're going to come to that once we cover the theory itself first. Now, the Spark transformer itself has two parts, the Spark FFN and the Spark attention. Now, in terms of what exactly is the difference between the both of them, we are going to have a very simple example in this case. We all know about the standard feed-forward network, the queries, the keys, the values, and using ReLU in this case as an activation function. And usually, this is the overall computation the computation cost that we have for this. We can also have that inherent sparsity using ReLU because you know the nature of it. But in the case of a Spark FFN, the thing we are differing is the splitting of the attention itself. Now let's get into that in a much more deeper sense. So let's cover this image first, of course. If we have a dense K information in this sense. We all know that KQE lies in the sense of query keys and values. So let's just consider it in the cases of key itself. What you notice in this case is that we divide K on the basis of a random metric R. So firstly, we have taken the query itself, we take from the start till the rth position, and then the second half is R to the rest of the stuff. So just to summarize, I know it gets a bit confusing for me as well. Like we have the original query and we have the original queries and all of the attention in a sense, and we are splitting it into two parts instead of it being just a single segment as itself in the original FFN, in Spark FFN. We are just simply splitting it on the basis of a random metric R, and we can see that over here as well. Firstly, we have the R into DFF, and the second half is D model minus R. So we can see it over here using the slicing index as well. We are just splitting it into two parts. So this is one of the major things that you have to take care of. One of the advantages of actually doing that is because we have already split it into two parts, we can now use GELU, which is proven to be much more better than ReLU, instead of ReLU itself to obtain the sparsity. So in this case, we're going to use GELU as our activation function, right? Now we're going to understand the physical significance of splitting this data into two parts. The input Q is split into two. We know that now, but why? We first contain the first R and then the rest of the dimensions as said in this line. What it actually does is it gives the network itself some understanding of how exactly is the data working, what is the right kind of activations in the start, and it gives it a very over-the-top understanding of exactly how things are working. And that leads it being worked as a low rank predictor. And that's pretty ingenious, sorry, not indigenous. That's pretty ingenious in a way. And what do we understand from this? We are saving our compute because we first use the first half that we have taken, and that length of the half in this sense can be anything. This R as a metric on the basis of what we are splitting our key, on the basis of what we are splitting our input, is up to us. It's a different metric every time, whatever we need to take. And the second part of what we have left after the split, we can use it directly and multiply it with V. we're saving our cost by understanding the data first a bit and then multiplying it with v later on. So that saves us the cost of doing that very heavy multiplication with the entire query set in the start. The best model quality is obtained when r is about the dimension of the model by 2, and we can also observe that it leads to a 4-time reduction from like the original equation, and it leads to a lot of optimization in this sense. I know it sounds as an idea which is pretty like common to understand, but it's pretty crazy how like simple things actually help out so much. And let's pick up the second part of the Spark transformer now, the Spark attention itself. The Spark attention has the same structure as our standard attention with the softmax itself, but again, because we split our input Q set in the start on the basis of our metric, we're going to do the same in this sense as well. The only difference in this case, as you can see over here, of course, the K1 belongs to our NCTX, and then K2 belongs to our D attention minus R, so the rest of the part, right? So we can see that over here as well. It contains first R rows and the rest of the rows from K respectively. Now, of course, we've split it into two parts. So we have two non-linear functions as activations now. The first one being softmax and the second one being soft plus. And lastly, now we're going to apply our statistical top K, which is also a new architectural thought that we have come about. And we're going to set all of the neurons which are below that threshold to minus infinity. So that is where we are actually bringing in that sparsity now. So in terms of results, of course, it leads to again a 4 times reduction in K attention. But let me just recheck if I've actually covered everything just to be sure about it. That's all. Yep. So now let's bring our attention to the statistical top K, the major thing this brings in terms of saving the compute. Just to remind you, top K itself as an operator takes a lot of compute in a sense of huge architectures because it has a complexity of about n log n if I'm not wrong. But the major drawback comes from sorting and considering top K, so we need the top K neurons. So of course we need to sort them first. So that leads to a lot of compute. So that's what we're saving over here by using a soft threshold. Now, a soft threshold in this case, we're going to use a quantile function to determine this soft threshold. Though to determine the soft threshold itself, it's comparatively easier. We have to have the mean, the standard deviation of the input, and here we are using the quantile function of the desired sparsity. 1 minus k by d in this case is here to define the desired sparsity we need. Like for example, in this entire paper, they've taken 8% as the desired sparsity, and that's what we are going to work with. And we're going to use q as a quantile function. We'll come to that in a minute. So firstly, of course, the threshold estimation. We come over here and we can see the quantile function. The quantile function works as an opposite or an inverse of the cumulative distribution function. The quantile function actually helps us to know what is the number of like data points that are above this percentile. So for example, if you need to know how many data points are above the 90th percentile or the 99th percentile, so you can see that it is the inverse of the cumulative distribution function that we all know from probability. Again, we're going to have this formula in this sense to determine this threshold that we are going to check. Now, let's get to the simple and very straightforward understanding what exactly is going on. Firstly, we split the input vector set into two parts, right? And that, on the basis of what we are splitting, decides is decided by us, and that is what is R in this case, if you remember from the splicing part. The second comes the statistical top K, and to determine that we need to have a flexible threshold instead of a hard coded as a fixed threshold as we have in normal top K. So once we have that statistical top K soft threshold aligned, we're going to apply the Gaussian distribution over it. And even if the data itself is not normal in a sense, but we use this to apply the central limit theorem and to understand the data much better, to understand and to have an evolving understanding of the neurons which need more attention and the neurons that need to be activated. And that's how we're going to ensure that 8% sparsity rate. So once we have covered all that, we're going to come to the results and the experiments. Firstly, of course, we can also cover this simple understanding of the difference between the statistical top K and the top K operators itself. And again, like I told you, this is a section that I don't understand much. So, I mean, you're welcome to, of course, give it a read itself. But yeah. So let's come up to the experiment itself. We're just going to cover up all of the results and then we're going to end it up, honestly. So we're going to use the Gemma 2 billion recipe, as I told you before. And the major things that we know from all this is that we're going to compare on the basis of ReLU square, and these are the number of steps that we have for the layer index and the percentage of non-zero, and the sparsity level in the spark attention and the sparsity level in the spark FFN. So those are the two differences. We can also, of course, again do revise. These are the basis of what we like divide the input set by. The quality. Surprisingly enough, of course, the quality does not decline. Even after having that 8% sparsity, we are able to have that near quality neutrality of the spark transformer along with the general pre-trained Gemma 2B model. So along with having like lower number of flops needed, as you can see over here. The sparsity. Do we have a sustained sparsity rate during the entire time of the training? And the answer is yes. Yes. Now, if we cover the next step, that is the inference efficiency. How much compute are we actually wasting in training and understanding this? Surprisingly enough, once again, we're going to save a lot of compute. So that's why we are going to consider this as a very foundational paper of something which may turn into something great over time. But this is something that I wanted to discuss. Lastly, let me just tell you about the applications of this spark transformer. In the case of a mixture of experts transformer, we usually use these architectures of mixture of experts, but they have a lot of complex algorithmic design and special hardware support required. So using these kind of transformers, which are specific and very special in understanding the FFN itself, so much so where each neuron in FFN is an expert itself with its own low rank predictor. If you remember, the first split of the query vector itself is a low rank predictor as well. And secondly, reactivating the activation sparsity. Like I told you, we have the two types of activation functions, ReLU and GeLU. Because of ReLU and its inherent quality of having sparsity in itself, it was used a lot in like sparsity applications. But over time, when we were enticed more with the idea of GeLU because it does not completely leave us with dead neurons, we moved way more towards GeLU as an application. But this is another sign of actually getting on with, again, good sparsity level. And honestly, that is all about this paper in this sense. I understand this paper is much more technical in a sense, and many of the things I don't understand myself. But I wanted to cover this paper because it seemed very interesting, and I wanted to understand a deep architecture for once. And I have understood it on a superficial level at least to understand how things are proceeding, but I'll get on with the deeper maths over time. So that is about it. Thank you for watching Open Steam. Hope I steamed your mind while learning and understanding. So thank you very much.